Hello, good evening, ladies, or wherever you are around the world. Greetings to all. This meeting is being recorded and will be distributed around IWF members. If you don't want to be recognized, please turn off your camera and close your name. Otherwise, it will be recorded and circulated according to GDPR and for Turkish laws, kişisel verilerin korunması kanunu. Thank you very much for all your attendance. So first of all, I would like to thank you for joining us tonight. And now it is a start of a series of discussions about artificial intelligence by IWF Turkiye. Artificial intelligence has become one of the most discussed topics in the world, as you all know. But I believe we are now entering a completely new phase of that discussion. For years, we spoke about AI primarily as a system that could analyze, recommend, predict, or even generate content. But today, we are beginning to discuss something fundamentally different. We are discussing systems that can increasingly reason, plan, make decisions, access tools, trigger workflows, and even take actions autonomously. In other words, we are moving from thinking AI to acting AI. And once systems begin to act autonomously, the conversation can no longer remain only a technology conversation. It immediately becomes a legal conversation, a governance conversation, a cybersecurity conversation, an ethical conversation, and ultimately a human responsibility conversation. That is why tonight's discussion is so timely and so important. Because the real question is no longer simply what can artificial intelligence do? The real question is how do we ensure the autonomy develops together with accountability, transparency, security, and human oversight? And perhaps even more importantly, how do we preserve trust in a world where decisions are increasingly delegated to machines? As many of you know, throughout my professional work in technology law, AI governance, data protection, and digital regulation, one issue has become increasingly clear to me. The future of AI will not be shaped only by engineers, and it will not only be shaped only by lawyers either. It will require interdisciplinary collaboration between technology, law, cybersecurity, ethics, governance, public policy, and business leadership. Because AI is no longer simply a software issue, it's a boardroom issue, it's a regulatory issue, it's a societal issue, and fundamentally a human issue. And this becomes even more critical in the age of agentic AI. Because when AI systems begin interacting directly with digital infrastructure, with calendars, financial systems, APIs, critical operations, and autonomous workflows, the risks are no longer limited to interconnect outputs, unfortunately. They may directly become incorrect actions. And that is exactly why discussions around authorization, auditability, human oversight, cybersecurity have become central to AI governance itself. Tonight, we are incredibly fortunate to have with us one of the leading experts in this field, Professor Dr. Aytül Erçil. who is also my dear sister and former president of IWF Turkiye. Her presentation, which I have the chance to listen at IWF Global Conference in London, beautifully explains not only the evolution of AI systems, but also the transition from traditional AI models towards autonomous agentic systems that are beginning to reshape industries, organizations, and daily life itself. And what makes tonight especially valuable is that we will explore the transformation of it not only from a technical perspective, but from ethics, security, and the future of society. Because ultimately, technology alone does not determine the future. The future is determined by how responsibly we design. Işıl, would you turn off your voice, please? The future is determined by how responsibly we design, govern, and use that technology. Would you please turn off Işıl's voice? The administration. The future is determined how responsibly we design, govern, and use that technology. So with that, it is my truly pleasure to welcome Professor Dr. Aytül Erçil and begin tonight's discussion, the legal boundaries of agentic AI. So please, Aytül.
Thank you.
The agentic area, the floor is yours.
Thank you, Çiğdem. Hi, everyone.
Sorry, Aytül, before you start, let me, Aylin, lütfen ses açılınca kapatabilir misin? Thank you
Tabii
very
Çiğdem Hanım.
Sorry.
Tabii.
Okay. Please, Aytül.
Okay. Hi, everyone. It's a great pleasure to be here tonight discussing about what's happening in AI these days. I would like this presentation to be interactive as possible. So please, at any time, stop me, ask questions. It's more important that we discuss rather than it's a one-sided lecture. So what I plan to talk about today is give the basics of AI foundations, sort of give a short history where we were and what's happening now, talk about the generative AI revolution, and then the agentic era that we're entering into. And then we'll talk about human-agent partnerships and challenges and what awaits us in the future. So the word AI was actually coined in 1956 by John McCarthy in a summer school. So it's not a new technology, actually. But if we look at the history of AI, for many years, there were some improvements, but not a whole lot of improvements until around 2000, where we started talking about deep learning. And I'll talk about what deep learning is in a minute. And then it started accelerating. And the next jump came in 2017 when researchers in Google founded the transformer model, which is the basis for the current large language models like ChatGPT, Gemini, etc. And now it's really skyrocketing. Now, AI has many subcomponents. Knowledge engineering is how to convert knowledge in books in a way that the computer will understand. There's robotic physical implementation of AI, voice recognition, natural language processing, natural language production, image processing, etc. But machine learning is really at the core of AI systems. So all the others, voice, speech, image, are like our sensors. Like in humans, we have 5 sensors. So those are replacing our human sensors. And machine learning is like our brain, which sort of learns systems and makes answers. So if we look at what machine learning is, you have some input data, and then you train a system to produce a desired outcome. So we learn the relationships in the data, dependencies, patterns, hidden structures, Just think of a small child. It takes a child about 2 years to start talking. So it really takes 2 years of training, which is a long time. I mean, we're expecting machines to learn everything very quickly now, but looking at humans, it takes us a long time, actually. It takes us a year to walk. It takes us 2 years to talk. Now, in machine learning, in old days, let me just talk about a simple example. There are classifier systems that classify spam mails from non-spam. So you would like, when you receive a mail, you would like the spam ones to go to a spam folder and everything else to go to inbox folder. The way this is done is, at least in old days, manually, some humans label every mail in the database, and they count how many words are there in the spam, how many words, which words appear in good mails. For example, in the data that they collected, the word Viagra was repeated 1,500 times. The word casino was repeated 1,400 times, etc. So then you have a probabilistic model which decides whether this is spam or not. So this all depends on your data. And if your data that you mark as spam doesn't contain these words, or for example, some of the words are there's free or enlarge or sale. I mean, those appeared a lot in the spam mails, but they could also appear in regular mails. So again, there were a lot of errors because the whole thing is based on probabilities. You need lots of data to be able to make accurate classification. So this was how the old systems were working. Now, if you look at human brain, we have a massive network of neurons. We have 86 trillion neurons in our brain, which is huge. I mean, we don't yet have any computer system that has such a huge network. Now, of course, people said, why don't we imitate human brains? So there was neural networks, and they were very hot at the when they were first founded in the early 90s. And the way neural network works is you have a network of neurons, and they're connected to one another, and you give an input, and you try to find all the weights of the connections to get the desired output. Now, if you have a very large network, to be able to train it, to be able to find all those weights, you need lots of data. You need tons of data. And that was not available. This is why for many years, there wasn't that much of an improvement in AI, because we didn't have enough data and we didn't have enough computing power to be able to train these networks. But then came deep learning, which is, I mean, there was a time in 2000s when computing power increased and when we had a massive amount of data. So they started having bigger networks, which they call deep learning. So we have much bigger neural networks, still not as much as big as human brain, but much bigger networks. But the amount of data required to train that is several orders of magnitude higher than old type of networks. So this was one big jump in AI, where when we had deep learning, sort of bigger networks, the improvement increased. But the thing is, for example, at Vispera, we develop AI solutions for retail industry. So we look at retail shelves and check for whether items are there, whether their layout is okay, whether the shelf space of competitors, etc. And the way to do that, we have agents, we have humans who manually label every item. This is a 1 liter Coke bottle. This is Cappy orange. This is Cappy peach, etc. So they manually annotate the data set. And then we recognize them. But then there's a new product. There's a new packaging. You go back to beginning. So you send it back to those people to label those. So this is a still human intensive process for teaching. I mean, the systems doesn't learn on its own. If you don't do any labeling, if you don't do any manual teaching, systems cannot learn on their own. I mean, to teach a child, if you just leave a child, bring the child to the world and don't speak anything, don't show anything, the child will not learn. It will either imitate people around them, or you verbally teach them. That's how you teach, machine learning works too. Now, to do that, I mean, for a smaller environment, like in a grocery store, this is doable. I mean, there are maybe thousands of items, but still you can manually label them. But think of doing it for the whole world, to identify millions and millions of objects around us, to label every object. Just think of chairs. I mean, there are hundreds of different types of chairs. So to label everything manually is very time consuming. And that's where the difficulty is actually for a long time. Now, there are, looking in the future, there are three types of AI: artificial narrow intelligence, artificial general intelligence, and artificial superintelligence. Artificial narrow intelligence is AI systems that are specialized in one area. They play perfect chess, better than world champion. They beat the world champion because they specialize in that area, and you train them and they are very good. Now, artificial general intelligence is they're specialized in all areas, so they can do anything that the human can do. And artificial superintelligence is sort of all humans combined. Now, where we are is somewhere between artificial narrow and artificial general. We're getting closer to artificial general, but we're not there yet. We have lots of very successful examples for artificial narrow intelligence. For example, we have tomato picking robots, for example. Recognize that a tomato is ripe and pick it. Or robotic surgery, or self-driving cars, or translation devices. You go to a country whose language you don't know, and it shows you, it translates it for you, etc. So even coffee fortune telling, it gives you a really nice coffee fortune. So there are all these specialized applications that work very well, but artificial general intelligence is not there. Even in China, recent development, they're developing first humanoid pregnancy robot that is capable of giving birth to a live baby. I mean, this is really sounds incredible, but they have the prototype. But again, it's not artificial general intelligence. Now, an interesting thing is in 2020, they asked experts when this AGI will be achieved, artificial general intelligence, and they said 50 years at the time. 2 years later, in 2022, they asked again, and this time they said 18 years. So in 2 years, we had the development of more than 30 years. And 2 years later, they asked again, now they say 5 years. So technology is moving very fast, much faster than even the experts expect. So, I mean, I used to think I will not see artificial general intelligence in my lifetime, but now I'm not sure. I could probably see it. Now, the next thing is Gen AI revolution. The first phase that I talked about was discriminative. So you classify, you teach the system, they learn to to classify things. But generative AI is a totally new idea where you can create new content. So you don't just classify existing content, but you generate new text, new image, new music, new code. So the difference between discriminative generative, I'll explain it with an example. In discriminative model, for example, you discriminate between cats and dogs. So given an image, you say whether this is a cat or dog. But in generative, you learn the class of cats. And then if I say, give me an image of a cat, it generates a new image of a cat, which may not even be in the database. So it learns the properties of what a cat looks like, and then generates maybe a totally new cat image. So that's really, that was sort of the first revolution. And there are three basic methods to do that. I won't go into details of, but just give a basic brief of what they are. Generative adversarial networks, transformers, and diffusion models. Generative adversarial networks are there are two neural networks that are competing with one another. So one network generates initially a random image, and the other one checks whether that's correct or not. So for example, say, give me an image of a cat. So it just generates a random image, and the other one checks whether that's cat. And it says, no, it's not a cat. So these are, so it generates a new one. And again, the other one, the police checks it. So this is iterated maybe millions of times until it has a very good image. So this is one technique. So there are lots of ways of, lots of good examples of images that are generated with that. The other kind is what we see most transformers, which is the large language models, which is again based on probabilities. So again, you have lots of data and you have a sentence, for example, the sky is very ... And then you calculate the probability of what the next word can be. So the probability of the sky is very blue is, for example, 80%. The probability that the sky is cloudy is 15%. The probability that the sky is very cheese is almost 0%. So, of course, you can see the danger here. At the beginning, we were having a lot of false results. It's because everything is based on probabilities. This transformer model is based on transform companies, from existing to this new AI native type. And that all depends on humans. It's done by humans. So I would first invest in humans.
Thank you so much. What a wonderful closing. Thank you, dear sisters, for being with us tonight, and looking forward to meeting once again in the near future.
Night, everyone.